Hey guys. We are going to be starting in our solutions, acids, and bases unit. Today we're strictly going to focus on the water and solutions part, specifically talking about solubility. We're going to talk a little bit about water. Water is what we use to make most of our solutions. So anytime we're dealing with a substance that is in aqueous solution or has that AQ after it, it's dissolved in water. Some things we've already learned about water throughout the course of this semester is that water has a bent shape. So if you remember the dot structure for water was like this. So it does have that bent shape to allow for interactions with other molecules. Water is polar, so it can be attracted to other water molecules by those dipole interactions. And it can also form hydrogen bonding. Some unique characteristics of water we're going to talk about is its really high surface tension and its really low vapor pressure. So talking about surface tension. So surface tension is that inward force or pull that minimizes the surface area of a liquid. So this is where you might have a liquid bead up. So say that you have a drop of water on a table. It's going to be a force pulling all of the molecule in towards the center. In water, this really high surface tension is caused by the hydrogen bonds. All liquids are going to have some form of surface tension, but water is particularly high because those hydrogen bonds allow all the water molecules to be attracted to one another. So it will hold a drop of liquid as a flattened sphere. So if you've ever done the lab where you do drops of water on a penny and it'll like create this large bubble on top of the penny until you add that one extra drop, that it can no longer hold the droplet together anymore. In order to decrease surface tension, you would add a surfactant to the water. So surfactant is any substance that will interfere with that hydrogen bonding between water molecules and break it apart. So maybe you put soap in the water, any type of oil or detergent in the water. So with that breaking apart those hydrogen bonds, it won't be able to hold as many water molecules together. This is something you can actually try from home if you have any type of dropper. You can do drops of pure water on a penny and then do drops of like dishwater on a penny. The dishwater will not be able to hold as many drops as pure water will because those hydrogen bonds have been broken apart. In terms of vapor pressure is the result of molecules escaping from the surface of the liquid and entering the vapor stage. So this is dealing with the evaporation part of water. So the hydrogen bonds in water hold the molecules together so they cannot escape the liquid as easily. This causes their evaporation to be relatively slow. So you could compare this if you put a cup of water in a windowsill. You know that the water will evaporate, but it's going to be slower than a substance like if you put a cup of rubbing alcohol near the window. The rubbing alcohol is going to evaporate more quickly than the water would. We also look at water as a solid, has special properties as well. So solid water, ice, is going to float in liquid water because it's less dense than liquid water. This is really unusual. Normally, the solid is going to be more dense than the liquid, and the solid would sink in the liquid. The reason that ice floats in water is because the hydrogen bonds in water hold the water molecules together in the solid state arranged like a honeycomb. So whenever the molecules link up, and I'm just going to sketch one of these real fast. there's going to be this gap of empty space, and these little dotted lines are our hydrogen bonding because we don't draw them as a solid line. So you end up with this gap of empty space trapped between all of these molecules. Well, what fills that empty space is air. So whenever you have those air pockets in there, that allows the solid to be less dense than the liquid, which is why it floats. That's something unique about water. Whenever we deal with reactions and stuff, most of our materials are in aqueous solution. So remember, aqueous solution means that we have water that contains dissolved substances, where we have our solvent, which is the water. So with aqueous solutions, we have the solvent, which normally is going to be water, which is the substance that is dissolving whatever minerals or chemicals we're dealing with. And then we have the solute, which is the substance being dissolved. So say you have a sore throat and you're making like a salt water solution to gargle. The water would be the solvent, and the salt is going to be that solute. Same thing if you were making like sweet tea. The actual tea would be your solvent. The sugar would be your solute in that case. In terms of solubility, um, excuse me, it skipped ahead. No, it didn't. Um, we're going to look at how we're actually going to dissolve substances. So solubility looks at how much can be dissolved. So there are three factors that determine how fast a substance will dissolve. First one is stirring. So stirring is going to speed up dissolving by bringing new solvent in contact with the solute. So if you're making sweet tea, you wouldn't simply dump sugar in and expect it all to dissolve, because only that top layer of sugar is actually in contact with the tea to be dissolved. But stirring kind of allows you to mix it to where new solvent is coming in contact with the solute. Temperature is also going to affect how fast something dissolves. So generally a higher temperature is going to speed up dissolving. So hot tea is going to dissolve more sugar than cold tea would. We also look at particle size. So the smaller the particles are, they have a higher surface area, more locations for dissolving to occur, so it dissolves faster. So using little grains of sugar is going to dissolve a lot faster than if you had cubes of sugar. In terms of solubility, we're looking at the amount of solute that can be dissolved in a given quantity of a solvent at a specific temperature and pressure to make a saturated solution. A lot of times we look at this in grams per liter or grams per 100 milliliters, something like that. And what we mean by a saturated solution, this means it contains the maximum amount of solute that can be dissolved with that quantity of solvent. So it cannot really dissolve any more than this. So this might be if you're making tea, if you keep adding sugar, eventually it will stop dissolving the sugar, where it can no longer dissolve anymore. And whatever cannot be dissolved will just kind of be sitting as a layer at the bottom. We also have unsaturated solutions. These are solutions that contain less solute than a saturated one, so less than it should be able to dissolve. So if you add more solute to it, they can actually dissolve more. So you can continue adding solute to be dissolved. We can also have mixtures of liquids as solutions. With these, we may not look at how much can be dissolved, but if they are able to dissolve in one another. So mixtures we look at is either being miscible or immiscible. So if mixtures of liquids are miscible, the two liquids can dissolve in one another in all proportions. So there's not really a limit to how much can dissolve. A lot of times these have to have similar properties in their intermolecular forces to be dissolved. So we talked about this with bonding and stuff like that. We talked about like dissolves like. So polar substances tend to dissolve other polar substances. Or nonpolar substances will dissolve other nonpolar substances. Whereas some things are immiscible. So these are liquids that are insoluble in one another, no matter how much the amount is. So think of like water and oil. You may be walking through a parking lot and you may see gas or oil floating on top of water because water's polar and the oil is nonpolar. So even if you stirred them, they would not actually combine and mix together. The factors that affect solubility, so for solids and liquids dissolving, solubility is affected only by temperature, whereas gas solubility is going to be affected by temperature and pressure. So the only one that's going to be affected by pressure is gases only. With temperature, generally as temperature increases, solubility also increases. There's only a few substances that will decrease, and most of these you'll notice will be gases. I'm going to show you kind of the trend of these in a moment. But with higher temperatures, we can also end up having supersaturated solutions. These are going to contain more solute than it can theoretically hold at that given temperature. So a lot of times, unless this is heated, it will end up crystallizing and forming into a solid. And this is kind of the process that gets used making rock candy and stuff like that. They heat up the water with the flavoring and the color and the sugar to where it's superheated, and as it cools, since it's super saturated, all of those crystals start forming and attaching onto the stick or string or whatever you're using to make rock candy. This is actually a process that you can do safely from home, and that's how a lot of people have used this before. So a lot of our solubility, we deal with reading these solubility curves. So this is a curve that you'll kind of be given to reference. If you notice, there's lots of lines that are different colors. Each different line is associated with a different substance. So like this dark blue line is for potassium chloride. The light blue line is strictly for sodium chloride. The yellow line is for lead 2 nitrate. So each line corresponds to a different substance. If you notice, the temperature is increasing going across the bottom. And then we have our solubility on the sides. This looks at how many grams can be dissolved in 100 grams of water, so in 100 milliliters of water. And as you notice, most substances, as the temperature is increasing, are going up. The only ones that you'll notice going down are going to be gases. And there's only one gas shown on this particular solubility curve. But how you would read this is it might say at 50 degrees Celsius how much potassium chloride can be dissolved in a saturated solution. So at 50 degrees, go up to potassium chloride. That's going to be about 42 or 43 grams. Or it might ask what temperature is needed to dissolve, let's say 20 grams of potassium dichromate. 20 grams of potassium dichromate's the K2Cr2O7. That needs to be at about 35 degrees Celsius. You could also figure out if a substance is going to be saturated, unsaturated, or supersaturated. So say that at 80 degrees, I have 20 grams of sodium chloride dissolved, and I want to know if it's saturated, unsaturated, or supersaturated. Well, 80 degrees and 20 grams is right here, which is below the line for sodium chloride. So that would be an unsaturated solution if that point is underneath that line. At that temperature, a saturated solution would be on the line. So that would be right at like 39-ish degrees, or grams, excuse me. Whereas if I had at 70 degrees, if I had 60 grams of potassium chloride, that would intersect here. That's above the line for potassium chloride. So that would be an example of a supersaturated solution. Go ahead and practice reading solubility curves, and then we'll pick up with some of the calculations in tomorrow's video.